Alright, here let's take a look at exponential decay. This is going to be another type of exponential functions. We previously covered exponential growth. Now exponential growth, if we were going to do a quick review, exponential growth looked like this. It came across an asymptote at 0, and then they grew very, very quickly. Now, the overall equation for exponential functions is y equals b to the x. And then there's other components that come into play, such as the a value here, the h value, the k value. And these work just as always if we wanted to look at it from that perspective. Yesterday we more so used the calculators or just evaluating functions to help us make the graphs. But these do move you left or right. These up and down. These affect the asymptote. And then the a value impacts, how fast things are growing or decaying. They kind of accelerate that as a stretcher compression factor. When you're looking at exponential functions that are y equals a times b to the x, to where there's no h value and no k value, your y-intercept will be 0, a, but h and k values mess that up. So, the best way to find the y-intercept otherwise would just be to plug in 0 into your function and then see what that evaluates to. But let's talk about decay. Decay is going to be similar to that coffee problem that we saw yesterday, where the coffee started off at 200 degrees and then we tracked its temperature over time. And it's going to give us some more information. Now, in order for decay to happen, or something special has to happen for our b value, it has to be less than 1, which that shouldn't be surprising. Yesterday we talked about how growth is when b is larger than 1, and b is what you're multiplying by over and over again. Decay would make sense that I need to be less than 1, because that'll cause me to lose value. But it also has to be greater than 0. And the reason for that is that the b value can't be negative. If you think about a negative number, when I start to multiply it over and over again, even exponents would cause it to be positive, odd exponents would cause it to be negative, and we'd get a really weird positive, negative, back and forth graph, and that would mess it all up. So in order for decay to occur, the b value has to be in between 0 and 1. So I call it pocket change, because it has to be, more than no money. You're not broke, but you also don't have a full dollar. So it must be a pocket change value, like 0.75, 0.25, 0.37. Any of those will work for decay. The domain will still be all real numbers. They'll move left forever and right forever. The natural asymptote will still start at 0 and then will be moved by k values. Decay look like this, with a natural asymptote at 0. K values will move that asymptote up and down though. And the asymptote helps determine the range. So let's take a look at this decay. Now let's first make sure to notice that 1/2 is really 0.5, which does satisfy the decay specifications. And they wanted us to make a table of values. And so what you could do, once again, to make this table of values is you could be figuring out what happens when you plug in different x's right here. And when you evaluate those, you get these different values. Now what's interesting about this, though, is when we are trying to evaluate with a negative exponent, so y equals 1/2 to the negative 2, remember that negative exponents cause you to take the reciprocal. So what really happens with this negative sign is that I'm taking the reciprocal, which would be 2 over 1, and then squared. 2 squared is that 4. So that's why decay start off really tall and then lose value. Because when I'm evaluating at a negative exponent, it takes that fraction or pocket change and makes it become the opposite, which is large. It's reciprocal. So you can see here the numbers were large and then they're shrinking and shrinking. Our b value on this particular case was 1/2. And you could see that each time I move from one spot to the next, I'm losing half of my value. So if you had $4 and you spent half, you'd be at 2. If you spent half again, you'd be at 1. Spent half again, you'd be at 50 cents. Spent half again, you'd be at 25. And this explains why even if we extend this, we have an asymptote here at 0. Because if you keep spending half, even if you have something very, very small, like that, a really small amount of money, or whatever quantity you have, and you chop it in half again, it's still not going to be 0, and it'll never get to 0. So that's why we have an asymptote right here on the x-axis. So as for domain and range for this graph, the domain is all real numbers. The range, though, will be y is greater than 0. Sorry, there should be an R right here for range. Because if you think about it, this graph will always be above the x-axis, so y will always be greater than 0. So here's a couple exponential growth graphs. And recall that you can type this in on your calculator or make a table. You know, if you wanted to make these by hand, when you're making your table, you're looking to plug in these different values, or you could type this in on your calculator and graph it that way. And it's possible to do this from shifts, but exponential functions, you know, we're more so safe to type them into the calculator. All right, now I'll give you a moment to type this in on your calculator or to go through and over again plug in your exponent as x and evaluate. I'll go ahead and fill in the y column on my table. And if you graph that into your calculator or you go through and you substitute in each x right here and evaluate, you will get these numbers. And then we'd be able to plot them. We have 0, 7. Now negative 113 is off the page. 1, 4. 2, 2.5. And if you keep plugging in other numbers, you will see that you do in fact keep decreasing. As we can kind of see this curve here. It will continue to decrease, but it's going to hit its asymptote at 1. All right, notice this k value of 1 moves up the initial asymptote from being at 0 to now that asymptote is at 1. Because even as this part of the function gets closer and closer to 0, that 1 always makes sure that it's approaching this red asymptote line. For this next one here, similar process. You could complete a table by plugging in your different values for x. You could also type this in on your calculator to see those same values. So I'll give you a moment to type those in and determine what those y values are, and then I'll fill in my table here. When you accomplish that, you'll see these numbers, and yours might have had the decimal equivalents, of 0.5 and then point that decimal and point that decimal as well. But what you'd see is that we have a y-intercept of 1/2. At negative 1, we are at 2. And then this one pretty quickly approaches its asymptote. This one's asymptote is right there on 0 because there's no k values here to shift it up. So our domain will be all real numbers, which it is for all of these. And our range in this case will be y is greater than 0. So that's graphing exponential decay. they start off tall and then decrease to their asymptote very quickly. What we're going to shift over here to look at is writing exponential growth and decay equations. This concept can get fairly complicated. We're going to stick with some more of the basic examples here. And what that's going to involve us doing is working with the equation y equals a times b to the x. All right, now a typically represents the starting value. Now remember that changes if you have an h or k value, and that's some of the situations that can get more complicated, but we're not going to cover those. But for the regular y equals a times b to the x, a is our starting value and b is the growth factor. So this is how we can write our own exponential growth functions. So here's how you do it. Step 1, take your growth rate and turn it into a decimal. You're going to then add that decimal to 1. Remember we talked about how for growth, your b value must be greater than 1. Multiplying by 1 keeps you the exact same. However, multiplying by 1 plus some percent growth can generate that b value that represents what we're changing by. So our goal here is to be able to estimate values with exponential growth functions. And we'll need our calculators for that. And you'll see after you do a couple of these that it's very basic. Here we have a population of 75 tigers is increasing at a rate of 45% per year. So our starting value A, 75 tigers. Now our growth rate, which is 45%, when we divide that by 100, it's 0.45. So our b value on this one is 1, because 1 keeps us the exact same. And then that 0.5 is what we're growing by, thus making the exponential equation 75 times 1.45 raised up to the x, where x is representing the number of years. So if we wanted to estimate this population after 4 years of growth, here's what we'd do. We need to type in 75 times 1.45 to the 4th power. Now, when we type that in on the calculator, it'll give us a number. So 75 times 1.45 raised up to the 4th power gives me 331.5, because we are estimating here. Right, so we're going to estimate, because we can't have 331.5 tigers, but we'd estimate somewhere around there that this population of tigers would be at 332. That's how simple it can be to write exponential growth functions. Exponential decay is going to work similar, especially involving its starting value A. That'll be the same. But now we're going to be working with not growth, but a decay factor. And its b value will be a little bit different. And remember that we saw up above that b values must be in between 0 and 1. So what we'll do to determine the b value is we're going to take the decimal and we're going to do 1 subtract that decimal to find our b values. So here we're going to estimate with exponential decay. So we have 3,023 elephants, nice population of elephants there, but they're decreasing at a rate of 19% per year. So when I do 19% as a decimal, it's 0.19. But if you think about it, if we are losing 19% of elephants, that really means we're still keeping 81%. And so that's how your b values work, is you're not multiplying by what you're losing, you're multiplying by what you get to keep. Right? So really the population is only 81% of what it was the previous year because it's decreasing at a rate of 19%. So our equation would be y is equal to 3,023 times 0.81 to the x. Now on this one, we're going to be able to figure out how many elephants would be left over if 19% of them are moving on after each year, and if this continues to happen for 7 years. So when we do this, you'll see that we are down to 691.5, so we can call that 692 elephants, which is a big drop off, right? You might be surprised to see that it went from 3,000 down to, close to 700. But, losing 20% of your population each year does start to make a difference. An exponential decay kind of looks like this. So most of the loss happens over time. Sorry, happens right at the start. Because when you're losing 20% of a large number, that's a lot of elephants. But when you don't have that many elephants anyways, and you're losing 20%, you're only losing a smaller amount. And this would eventually asymptote down to 0, to where we would have 0 elephants total. So that's how you can create and write them. If you wanted to see more examples on this, you could pause the video and try it again. We're going to see some more scenarios here as well, where we use exponential growth and decay. So many exponential functions will be modeled by y is equal to a times 1 plus r, right? Because that helps us determine our growth. We did that on the last page. We did 1 plus our rate to the t. This is mostly used in banking and finance or investing. Where a is the starting amount, r is the rate as a decimal, and t is the time period. So let's talk about some different interest rates. So maybe this is for stocks or a bond that you have bought. Savings account aren't going to give you interest like this. But 4.2% is a decimal, would be 0.042. 11.6 is a decimal, would be 0.116. So let's take a look at exponential growth. It says, now imagine that we deposit $2,000, our starting value A, and we're going to use the two different interest rates to figure out how much we would make in 10 years and 30 years. So our equations on this would be y is equal to our starting amount, which is 2,000, our rate, which is 1, because 1 multiplied by 1 keeps us the same, and then the 0.42 as our 4.2% raised up to the time. So for this one, let's check and see how much money would we have if we left it there on that interest rate for 10 years. We can type that in on the calculator. So if we left $2,000 with that interest rate for 10 years, you'd be up to $3,017.91, which isn't really that big of a growth, especially waiting 10 years. But let's see about 30 years. If we have 2,000 and we're waiting 30 years this time, typing this in on our calculator would give us $6,871.66. So much larger, right? But we had to wait much longer in time. Now, with this, $2,000 really isn't that much of a starting amount. When you're saving for retirement, and you're letting it sit there and gain money for 30 years, you're going to want to make sure that you're starting with more than $2,000 in that account. And that's why when you're saving money for retirement, you pull money out of each paycheck so that you can keep making that A value be larger and larger. But let's check it also with a larger interest rate. So still the same $2,000, still the same 10 years and 30 years, but this time we have a much larger interest rate. So 1.116. 1.116. So it's the same amount of time as above, but this time we have a much better interest rate, one that you might fine if you're doing really well on stocks for a long period of time. With a higher interest rate, even after only 10 years, we're up a good amount. You know, this one's almost up fairly close to how long that one took in 30 years. But if we are getting a really good rate, you know, that 11% for 30 years on $2,000, this time it's 53,821. So now we're talking about some big changes. And if you remember what growth graphs look like, they look like this. You know, so that's why there wasn't too much change after 10 years. We didn't have enough time for this curve to get high. But as we wait for 30 years, now we're getting up onto the growth that's starting to be much more steep. Now, the reason the one up above didn't grow very fast is because with this B value only being 1.042, we're not really changing that much. So this curve would eventually swoop up, but it's going to take much, much longer. When you have a larger B value, your curve starts to curve up much sooner. So that's why you want to make sure you're getting high interest rates on stocks and bonds or whatever you're investing your money on, because 30 years at a high interest rate got me 53,000, while 30 years at a low interest rate only got me, close to 7,000. Another thing that we can use our calculators to do is figure out how much time it would make to acquire a certain amount of money. Because say you are saving, or say I'm saving up for baby Owen, and I want him to have $4,000 to buy a car by the time he's 16. And I want to see if this is going to work. And let's assume that I have learned how to use stocks, which I do not know how to do, but I can ask Mr. Chitwood in his finance and literacy class. So let's assume I'm getting the 11% interest rate. What I can do is figure out, if I invest $2,000 at that 11.6% interest rate, how long will I have to wait? In order to do this, we're actually going to need to use our calculator. And I'm just showing us this for fun, basically. We will learn actually a way to do it officially without having to make graphs later on in this chapter using something called logarithms. But right now, even though we don't know how to solve this equation, because I haven't taught you how to solve for variables that are in the exponent, you can actually solve any equation that you want by graphing both sides into your calculator at the same time. So if I go into my calculator and I graph those two equations, what I will get is a picture that, if you set your window right, will look like this. It'll have a line going across at 4,000. And then we'll start to see the exponential growth curve, this guy, starting to rise up. And that curve would look like this. It's starting at 2,000, because that's how much money I'm saving for baby Owen now, and it would start to curve up and eventually cross it. And if you use second trace and then go to the option that's called 5 intersect, you can figure out where those two curves cross. And what that'll allow me to do is figure out the amount of time it would take, right? Because this is my time axis down here. And when I did second trace, it told me that this coordinate point was after about 6.3 years, I would be up to $4,000. So that means if I wanted to start saving for baby Owen to have money to buy a car, or maybe even he wanted to start saving money, he's going to need $2,000 when he's about 10 years old. That way, when he's 16 or 16 and a half, he can have the $4,000 that he needs to get the money. So he'd have to wait about 6.3 years. Well, we are later going to use logarithms in this chapter to solve for that without having to make a graph. But this was just a fun little way of seeing how we could use exponential growth to find out some financial information.